Hi, in this video we're going to talk about the charging behavior of our RC circuit. In the last video we saw that the differential equation that describes our RC circuit is this one, and we were interested in looking at the solutions of this. So as I mentioned before, the solutions of this circuit depend on the initial conditions. So first we're going to assume, if we remember how our circuit looked like, we had our circuit and we had a switch with our resistor and our capacitor. So first we are going to assume that the switch has been open for a long time, and therefore the capacitor has had a lot of time to be able to discharge. So the capacitor is in its discharge state, which means that the initial voltage of the capacitor at t equals 0 is 0. And then we're going to close our switch so that voltage and current will suddenly start flowing through it, and our input voltage will simply be the amplitude of the pulse that we have here. So those are our initial conditions, and with those initial conditions, the solution for the voltage in the capacitor from this differential equation is V C of t is equal to the input voltage times 1 minus e to the minus t over tau. In this case, tau is called our time constant and is equal to R times C. So this is basically the solution. And there are, of course, many ways of solving this differential equation. From, one of the most common ones that we electronic engineers like to use is by using the Laplace transform. That is outside the scope of this course, so you'll just have to believe me that this is how the equation looks like. So what does that mean? If we have, for instance, we can plot this response. I'm going to make a nice plot here. We have time and we have voltage here. So if we imagine that our input voltage was 0 for a long time, and then at some point we switched it on at t equals 0, and then it had certain voltage value, which in this case we're going to call Vin or Vi for input voltage. So that's how our input voltage would look like. And what will happen with the capacitor when we basically plug that equation in MATLAB and put many time values here and put values for R and C, we get a curve that looks like this. At the beginning, everything was switched off, so everything's 0. And then as soon as the voltage source is switched on, my capacitor will start charging slowly with this curve. Eventually, it will also reach the input voltage that we had here, and it will be charged up to that voltage. Now, I don't think we can see this line very clearly here. There you go. Like this. So it's a nice exponential curve that looks like this. Now, as I mentioned before, tau is equal to RC. It's our time constant. And if we look at our voltage at the time equals 5 tau seconds, our capacitor will have charged to approximately 99% of the total charge. Of course, this curve is asymptotic, so it will actually never ever reach the input voltage, but we assume since at 5 tau it's charged to 99% of the total charge, we assume that 5 tau plus or at times greater than 5 tau, our capacitor is already completely charged. Now, we can also calculate the current in our capacitor because we have the characteristic equation, which is our current in the capacitor is equal to C times the derivative of the voltage, right? So we can just take this equation and plot the derivative. So IC of t will be C times the derivative of V in times 1 minus E to the minus t over tau. And we can calculate the derivative. So V in will be out because it's a constant. And then we have here a sum of 1 minus the derivative with respect to time of e to the minus t over tau. Of course, the derivative of a constant is 0. And the derivative of our exponential is the derivative of our exponent times the exponential times c times minus 1 over tau times e to the minus t over tau. So, there's something wrong here. So minus, V in times C over RC times E to the minus t over tau. Because tau is RC, this C goes out with this C, and then we have IC of t equals minus V in over R times E to the minus t over tau. And there's minus here. That cancels this one out. And we get that here. So this is the equation that describes the current in our capacitor. Now, we see very clearly here that we have here V in over R, which V in is a voltage, and a voltage over the resistance is current. So this is a current, and it's times e to the minus t over tau. So how does this current look like if we look at our graph here? For t equals 0, when I switch on the voltage source, I have e to the 0 here, which is 1. So for t equals 0, I have the maximum current. And then it will slow down as the capacitor charges over time. It will go back down and down and down until it reaches 0. So the current, before we switch on the voltage source, is also 0. Nothing is flowing in the circuit. The circuit's open, so nothing's flowing. So it's the current 0. And then suddenly, as soon as I switch the voltage source, my capacitor, the current in my whole circuit goes up to, I'm going to put here V in over R as current, goes up to the maximum current that can flow, which is the input over the resistance, and then it will slowly go back down until it reaches 0. This is not a very nice curvy curve. Let me try again. That's nicer. Like this. So there's a few things that we can look at this just by looking at this. The first thing is we know that when I switch on the circuit, my current goes to VI over R, which basically means that when the capacitor is discharged and I switch on the voltage source, my capacitor is acting like a short circuit. Yeah. So basically, my capacitor is closed there for a short moment so that I can have my current here. By Ohm's law, we calculate that the current here is V in over R. Yeah. So when the capacitor is discharged, it acts as a short circuit. And the other thing we can see is that when the capacitor is completely charged at, say, t equals infinity, the voltage in the capacitor is equal to the voltage, to the input voltage, right? So what does it mean? When the capacitor is charged, here I have V in, which means that there is no voltage drop falling into R, because otherwise Kirchhoff's law tells me that V in would be VI minus VR. But if VR has to be 0, so that VI equals is the same here and here, right? So it means that there's no current flowing through R, so that R times 0, which is the voltage, is equal to 0. And that means that my circuit is open here. So when my capacitor is completely charged, it acts as an open circuit. So yeah, those are the equations that describe the charging behavior of the capacitor. That's the voltage and the current. And those are the equations that we use to calculate what the charging and discharging behavior of the capacitor are. And these basically are the solutions of the differential equation with the initial conditions I described at the beginning of the video. So in the next video, we will talk about the discharging behavior of the capacitor. Thanks for watching.